let's start now. Hi, my name is Markku from Google Cloud. I am based in Tokyo. And without any further ado, let's get started with the presentation. Today, I'd like to show you how to improve machine learning model quality by working with the data. So I have a hypothesis that in order to make a machine learning model better, the neural network that is actually the brain literally behind the machine learning model, there's a couple of ways. Well, there's many ways, but including these two, you can work on your data. More training data, we let the neural network run more training cycles and see examples. So neural networks learn from examples. So the more examples you can give of your training data, the better your machine learning model quality will be. So more data is better. Second one, better data is better. So in some cases, you may need to help the neural network focus looking at the right part of data. So basically fixing the signal to noise ratio in data. And in order to actually create a nice machine learning model, I'm going to take the lazy developer route and use something called AutoML. With AutoML, you don't need to be a data scientist. You don't need a PhD in statistical mathematics. You can let a service create a custom machine learning model for you. So basically, AutoML is one way of creating machine learning models that accelerates developer speed. Non-machine learning experts can create custom models with something called the meta learner. That's on the left. So literally, we have machine learning models creating machine learning models, and they can do it much faster and try many more things than humans could do. So basically, by using AutoML, all we need to do is provide example data, let the system figure it out, try different things, and come up with a model that works very well with your data. So let's start with the first hypothesis, that more data is better data. Let's test this with a question that came to me from one of our customers who are working for a very large bank here in Asia. So they told me that they have a business problem. They have hundreds of thousands of documents, physical papers, that are chopped, stamped by different stamps, different companies and entities stamps. And today they need to manually check which stamp was used to chop which documents. So the question they posed was, could AI, machine learning, help them identify these stamps on the documents? Okay, so that's the problem. So how do we go about testing this? Well, with machine learning, you need labels. Labels are what the machine learning model will try to identify, like classify. This is the first stamp, this is the second stamp. And then we need labeled images. We need training data for AutoML. So somehow we need to chop some documents and use those as training data. Because I don't obviously have those bank documents, they are confidential, I needed some way of creating synthetic or generated training data. So I started with this idea, what if I download some pictures of stamps? So I went to the internet and I downloaded these, you can see on the screen, 9 open source stamps. And then I needed some pages. So I had some stamps, digital stamps. I needed some pages. I went to Project Gutenberg that hosts the free ebooks, and I downloaded Sherlock Holmes and Pride and Prejudice, 2 rather long books. And I had, after that, 385 images of pages. Okay, so I have stamps, I have pages. What do I need next? We need to generate training data for AutoML. So basically, we need to give to the service examples of pages stamped with different stamps. Remember, I had 9 different stamps. How do we do that? And how many? Well, one thing I wanted to do was to test AutoML. The hypothesis is that more data is better machine learning quality. So I wanted to do a head-to-head comparison of 100 test images or training images versus 1,000 training images versus 10,000 training images per stamp or per label. So 9 stamps times 10,000 is 90,000. So basically I needed to have 90,000 pages chopped with different stamps. I'm not going to do that manually. So let's do a bit of Python. So I did a bit of Python coding, very rudimentary, and I created a couple of little utilities. The first utility takes the stamp images and rotates them 360 degrees, saving each rotation as an image. Because my idea was that the stamp can be at any angle on the page. And then we need to stamp the pages digitally. So I wrote a second utility that takes a random page from Pride and Prejudice or Sherlock Holmes, takes a random stamp, randomly rotated, and overlays the stamp on the page. And then we need to use this as training data. So let me show you first what this can look like. How to create synthetic training data. So let me very briefly show you first of all that I have here these images of pages. These are pages of the book Pride and Prejudice. So we need to stamp these pages. And then how do we stamp them? I generated these rotated transparent images of stamps. Okay, so I have pages, I have stamps. This is the approved stamp. So next what we can do is run the utility that will take stamps, take pages, stamp them as often as we need. So let me now first ask the utility to stamp each stamp 5 times on random pages. I executed the utility, the output comes here. And then if I start opening these pages, you can see that, okay, first we have 5 approved stamps on random pages. Then we have 5 do not copy stamps on other pages. And then we have 5 draft pages. So all I needed to do to generate these 90,000 training images was to change this command line utility parameter, and instead of 5, I put there 10,000. So then I ended up with 9 stamps times 10,000 images. And what do you do after that? After that, I went to Cloud AutoML. And here's an example of Cloud AutoML where you can upload training images. And then all you need to do is to click train, and it will create the machine learning model for you. You can then evaluate the model. And then when you're happy with the model quality, you can export the model. Now, you can either run it in the cloud, Google has a service for that, or if you want to run it on physical devices, on premises, you can export it. You can export it as TensorFlow or container, which is very common, or Coral. So Coral is Google's EdgeTPU, machine learning accelerator. So little hardware chip that can run machine learning very quickly and fast and efficiently. So you can export the machine learning model you generated in different formats. So I exported it with Coral. Okay, the story continues. So we generated these training data, we trained the documents. So the utility was able to create these synthetic training data. You can see some examples here, as well as a CSV file that tells the AutoML service which training pages are for what label, what stamp. And after that, I could compare. I made 3 trainings in AutoML, one with 100 images, training images per stamp, the second with 1,000, and the third with 10,000 examples. And I'd like to show you the results here. The worst case scenario is always the one we should look at here. It's not good if something is always 100%, but with 100 training images per stamp, the worst performing stamp classification was only 37%. So one of the stamps, called do not copy, only had a 37% success rate in being recognized. It's not good. It's not going to meet anybody's business targets. Okay, then I trained 1,000 images per stamp. And suddenly, the worst case scenario went up to 66%. That's better. But I'm an engineer, I'm silly, I'm curious, so I created 10,000 training images per stamp. I wanted to see if it improves even more. And yes, it went to 78%. So at some point, you're going to hit the law of diminishing returns, but at least until 10,000, if you can generate synthetic data or generate training data programmatically, you should try with more data. Easy. Then when I evaluated the model using the final version, the 10,000 training images one, the success rate was pretty good. So it was 99.9% confident for this page on the left that that's the bestseller stamp. Yes, it is. And here on the right side, you can see an example of a slightly worse performing do not copy or draft stamp. So the actual draft stamp used was called draft. You can see it says draft there. The confidence of the machine learning model was 77%, so lower, but still relatively high. But it thought that maybe there's a 22% chance that it's the other stamp called do not copy. So then you have to do testing, and you need to find the performance, and you need to have a cutoff value, a confidence score that you are happy with, say above 70%. Then you trust the result. What do you do with the results that are lower performing? Well, you collect those results, you analyze what went wrong, and you most likely use that information to retrain a better performing machine learning model. So then I went back to the people at the bank, and they were like, yeah, that's cool. In theory, your simulation works, but does it work in real life? Good question. So then I exported the model to Google Coral Machine Learning Accelerator. You can see the picture here on the left. That's one of the form factors. It's a USB stick that has the machine learning accelerator chip inside. So you can run the machine learning model, the neural network, inside that chip. And then you need a host computer. I just used a Raspberry Pi in this case. So now I'd like to show you that here on my table here, you can see it's a bit hard to see. I have a Raspberry Pi computer there. That is the host that I use for the next demo. And you can see the Google EdgeTPU accelerator here connected with a USB cable to the Raspberry Pi. So that's the machine we are going to be using now. And this is now the actual output of the HDMI port of the Raspberry Pi. So I wrote a little app on the Raspberry Pi where we can test things. So let's try first with the standard machine learning model. I will use the MobileNet model, which is one of the basic models. And as we now pass the Raspberry Pi camera feed through the EdgeTPU, we can see what the Raspberry Pi sees. And on the top of the screen, you can see the EdgeTPU inference results, machine learning inference results. What is the label that the machine learning model thinks that it sees, and what is the confidence? So if I put my little remote control keyboard here, you can see it says, yeah, remote control, remote, something like that. And you can see the inference time is about 5 milliseconds. If I put my lights remote control here, you can see that, yes, with the standard model, it can see that's most likely a remote controller. So that works fine. So that's a standard model. However, if I take one of the stamps that I generated for the bank, it will not know what it is. So we need a custom model. So how do we get a custom model? By switching the model we are using on the device. So if I switch the model, I load the custom model that we made for the stamps to the unit. Now it has loaded that model. Now, when we present these stamps to it, let's see what happens. Yeah, it's a bit struggling. It's not that sure, but yeah, maybe it's paid. And if I change to another one, now you can see that, okay, now it's pretty confident that stamp is called do not copy. And let's have one more. Let's show it the approved stamp. And yes, now the machine learning model is pretty confident that that stamp is called approved. Okay, so live test completed. So that seems to work fine. All right, so that was the first hypothesis. Does more training data potentially improve machine learning model quality? Yes, it did. And we also showed that at least in some cases it works in the real world as well. Now with that, I'd like to follow up with the second hypothesis. My second hypothesis was that sometimes you need to help the machine learning training by fixing the data before you train the model. And actually, I will use a real-life customer use case here. So one of our customers called Kyocera in Japan, very traditional, old established company, they do manufacturing, small and medium batch manufacturing of components for other businesses. Until now, they have been evaluating, inspecting the quality of these production line components manually with humans. That is obviously slow, it's error prone, it's hard to train the experts, there's generation change. So Kyocera asked us, could we use AI to let the people, the humans, focus on more value-added tasks in the company, and could we automate this task of visually inspecting the quality of the components with AI? And of course, the quality has to be at least as high or higher than humans and has to be fast enough. So let's see. These are, I will remove myself from the picture so you can see better. These are some of the actual images from the Kyocera manufacturing line. You can see that in the images that are taken top down at the production line, the components that we need to inspect are jumping around. That's just because the production line is moving underneath the camera. The component we want to inspect is the one in the middle. You can see it's jumping around, it's sometimes rotated a little bit. So there's a lot of kind of noise in the picture. And you can also see other components partially in the camera image, which is confusing the situation. So what happened was that the customer just tried using AutoML by itself with those raw images from the camera. They created this model, but the results were not that great. The worst case scenario was only 14% success rate. And with a little bit of tuning, 56%. So still lower than humans. So that's not good. So we needed to do something. So I was the engineer assigned to this case. So I was thinking, scratching my head, drinking a lot of caffeine, crying, trying to figure out how to do this, kidding about crying, but struggling, sweating. I decided to try pre-processing the data. What if I could help the machine learning training focus on the object in the middle? So what I did was first I did a crop. So I went from this big picture, this is the original frame, and I found a crop place in the image that if I cut the image here, I will cut away the other components that are partially visible, but I never cut away the actual component that I'm inspecting. Okay, this is step one. By the way, there you can see one of the defects. So ultimately, the machine learning model was supposed to detect, are there defects like that somewhere in this object? And those kind of blemishes can be anywhere. They are tiny little dots. So the AI is supposed to detect, are there little dots like that, or is the component fully clean, which means it's not defective. Next, what I wanted to do was to get rid of the background. The background is a kind of tray where the object is sitting. So I found some Python image processing filters that when I applied those filters, the background pixels went to 0. They went to black. Black pixels have value 0.0.0, so they don't have any value. So conversely, now after this filtering, the only pixels remaining in the image that have value belong to the object that we are interested in. Okay, that's good. Then I was able to apply another Python image filter, which is an edge detection filter. So because the background pixels are gone, they don't exist, it's easy for the filter to figure out what is the edge. Then we were left with this. However, this is actually a point cloud. So those are not lines, they are dots. What I wanted to do next was then to rotate the object horizontally. So for that, I applied something called the Hoff transform. So with this point cloud of edge pixels, by applying a Hoff transform, the Hoff transform can detect straight lines. Okay, so when I have these lines, I was able to calculate the rotation angle of the object, deviated from 0 or horizontal. So then I simply counter-rotated the object back to 0 so that it was horizontal. And by the way, I made sure that the rotation of the image used the original pixels, because you don't want to do destructive changes to the data. So all these steps that I do are non-destructive, including the rotation. And then I did one more edge detection, and then I was able to crop exactly on the edges of the object that is now flat. So we went from that confusing image to these images, and now you can see here the processed or pre-processed images. When I fed these pre-processed images to AutoML, this was then the result. So the model quality was 95% and 98% accurate for detecting broken or not broken components. And using the machine learning accelerator chip EdgeTPU, the average inference time for the neural network was 9 milliseconds. So this was able to meet the customer's strict requirements for the production quality. So now I'd like to very briefly show you, with a couple of minutes remaining, a live demo of this. So let me go back here and very briefly show you that. I will run first the pre-processing against one of the images. So here is one of the original images from Kyocera, and if I run this pre-processing script in debug mode, where it outputs all the intermediate steps, you can see them appearing here. So the script took the original image, it did the background removal, it did the edge detection, counter rotation, Hoff transform, finding the lines, and then finally cropping the rotated object. So this is then the output image. And when we give these output images to this guy here, the Google EdgeTPU, here on this window here, sorry about the confusion, on this window here, I'm logged into the Google Coral development board that has the Kyocera images, and it has the EdgeTPU, and it has the model that we created for Kyocera. So let me, as my last step here, run inference against a few hundred Kyocera raw images using this machine learning model, and let's see what happens. So first I run the inference against all known to be good components. So you see here the image name, and then the inference result label, okay, okay, okay. So the machine learning model was saying these are okay, these are not defective components. And then we have the machine learning model confidence, 92% here, and then the latency, 7 milliseconds, 8 milliseconds here. However, machine learning is never 100% zero. So if I scroll back here, we can see that here there was a mistake. So here the machine learning model said that this is a broken component when in fact it wasn't. So it's not 100%, it was around 95% accurate. And very briefly, if I run the same test against all known to be defective component images, this is the result. So most of the time, the machine learning model said, yep, they're broken, they're broken, they're broken. Sometimes it makes a mistake, it says, no, it's not broken. But then when we look at the machine learning model confidence, it was not as confident, only 62 and 69%, where normally it's over 80% confident. So you can have this threshold value where you trust or you don't trust the machine learning model quality. Anyway, that was a live demonstration against raw data from Kyocera factory, detecting both broken and not broken components. There we go. And just to recap what I did, on this Coral dev board that you can see on the right, the CPU, which is an ARM CPU in this case, did the pre-processing from the raw images, and then it came up with this pre-processed focused image of the component. And then this focused image of the component was given to the EdgeTPU machine learning accelerator that runs the neural network, very simple classification case, broken or not broken component. So it looks at this focused object, and the result you get out is okay or not okay with a confidence value. That's all from me. I really hope that you enjoyed this look into how data pre-processing can help improve machine learning model quality.